Okay, this is for Astronomy 320. The date is July 21st, 2020, and we're skipping ahead to Chapter 15 on the Sun. And basically, you're supposed to have a quiz today. Today's Tuesday. I totally forgot about it. Your quiz will be on Thursday, the regular time, whatever time our class starts, like 9 o'clock. And it'll be on this one right here. Remember this one right here? We haven't had a quiz on this. This is what we're supposed to have the quiz on today. And I totally forgot. Alright, so it'll be on Thursday. You guys will have a quiz, and I'll send out a blast email that you'll get way before you hear me talking about it here. But anyway, this will be the quiz on Thursday based on this material right here. Okay, so now we're on Chapter 15, the Sun. This is a data table taken right out of the textbook. Okay, so the data is over here for different things. Obviously, since you get to use this on a quiz on an exam, I'm not going to say you don't have to memorize this because you've got access to this. All right. So anyway, there's everything about a lot of stuff about the Sun. Okay, here's some more stuff about the Sun. The Sun is a star. All those stars you see in the night, okay, they are very, very far away. I think the closest one to the Sun is like about 3 or 4 light years away. So they're all very, very far away from the Sun. Okay, the Sun is the closest star to us. That's why it's so important to us. It's the center of the solar system. Everything in our solar system, well, most things in our solar system orbit around the Sun. Obviously, you've got moons orbiting planets, but just about everything else orbits the Sun. The Sun provides almost all the energy that exists in the solar system. The only exception would be if you go out at night and you look at a star, okay, that energy that caused your rods and cones in your retina to fire and send signals up to your brain, that came from something besides the Sun, but everything else comes from the Sun. The Sun is about 5 billion years old. It has about another 5 billion years left to go. It's fusing hydrogen into helium in its core, and eventually it's going to run out of hydrogen. So hopefully by then our predecessors will be able to figure out some way to tow the Earth someplace else and save Yosemite and the Grand Canyon and all that. The Sun is by far the largest object in our solar system. About 1.3 million Earths could fit inside the volume of the Sun. That's how much bigger the Sun is compared to the Earth. It's got over 100 times the diameter of the Earth. And if you do the volume calculation, you end up with about 2,900 something million Earths could fit into the volume of the Sun. The Sun is actually a very average star. Here in Sacramento, because of the light pollution, you only see the brightest stars. All the stars you see at night here in Sacramento, they are way bigger, and if they're the same distance from the Earth as the Sun was, they'd appear way brighter. Life wouldn't even be possible on the Earth because it'd be too hot. We'd have to be further and further away from that star in order to survive. Okay, so it's a very, very average star. And there's a lot of stars just like the Sun. They're the ones that are harder to see at night when you go to someplace really, really dark. The stars you can see in the sky at night from Sacramento are all much bigger than the Sun. The Sun, as far as we know, this is one thing the Sun has on all the other stars, as far as we know. Those other stars, what are they accomplishing? They burn bright, but are they really doing anything helpful? Because as far as we know, they're not supporting any kind of life or anything like that. Only the Sun, as far as we know, supports life. And then these are the gases that make up the Sun. You can see it's 92% hydrogen, 7.8% helium, and the rest are just trace amounts. Well, that's not surprising because hydrogen and helium are the most abundant elements in the whole universe. Hydrogen is just basically a proton. Helium's the most common type of helium is 2 protons and 2 neutrons, so they're the simplest. They're at the very beginning of the periodic table, and they're primordial, meaning that they're here right from the beginning of the universe. The corona and the chromosphere. So here's the Sun. So you've got outside, the farthest part out here is the corona. There's the corona right there. That looks like that. It's all spiky and stuff. You say, well, I don't see, the Sun doesn't look like that. It looks like it's like a pretty round. Well, that's because we can't really see the corona because the photosphere is so bright. It's the photosphere that dominates. But not just the corona is outside the photosphere, so is the chromosphere. But both of those are dim compared to the photosphere, so we actually see the photosphere. It overwhelms this part of it that the corona would be. Okay, the corona and the chromosphere are the outer parts of the Sun, but not the part of the sun we actually see when we look at the sun because of low density. The photosphere is the part we actually see. Then you've got inside of here, you've got this thing called the convection zone. Convection means warm material rising, cool material falling. Okay, we might get more in depth in this depending on what your book does. But anyway, warm material's down here and it starts to rise, goes to the surface, and it puts out radiation. It goes towards the earth and everywhere else, and then when it cools, it falls. So you got this like churning going on, this complete cycle going on of warm material rising, then it cools off when it releases its energy, and it falls back down, warms up again, and around and around. This is the radiation zone. Okay, the radiation zone. This is so hot, electrons are not combined on their atoms, so there's nothing to absorb the radiation, so it can get right through there, no problem. Up here, it's cooler, so the electrons recombine, and that's why the energy gets absorbed at this point, and that's why you got to use convection here. The convection zone's here, then here's the radiation zone, radioactive zone they call it here. Radioactive zone, I call it the radiation zone. Okay. Okay, so you got the convection zone, moves the energy to the surface through convection. Radiation zone moves the energy from the core to the convection zone through radiation. The core, see there's core right there, the core down in here, this is just out of your book. The core here, this is where the business takes place. This is where we're fusing hydrogen into helium. The helium that results has less mass than the hydrogens that went into making that helium, and as a result you've got leftover mass which gets converted into energy. Einstein's E equals mc squared, energy equals mass times the speed of light squared. So that's where the energy is being generated by the sun, right in here, and we got to get it to the surface, and it takes an incredibly long time, like thousands of years, for that energy to get from here to here. So the book starts talking about the corona. I don't know why. I thought it was going to talk about the corona and start talking about the photosphere and everything else, but it doesn't. The corona is the outer part of the sun's atmosphere. So this is an ellipse. This is the moon passing in front of the sun, so it blocks off the photosphere. So now we can see the corona, okay? Now you can see the corona when the moon passes in front of the sun and blocks off. It's like, even though the moon's a lot smaller than the sun, the moon is a lot closer than the sun, and it's just a perfect, mathematically perfect fit for it'll block out the sun, the photosphere, and in some cases even it'll block off the photosphere but not the chromosphere, so then we can see the chromosphere depending on where it is, how close or how far it is from the earth at that time. Okay, the corona is the outer part of the sun's atmosphere. It is best seen as in the photo to the right when there is a solar eclipse. Moon passes in front of the sun. The moon blocks the photosphere and the chromosphere, and the less dense corona can be seen. Okay, due to the extreme temperatures found in the corona, extremely energetic electrons are able to escape the gravitational pull of the sun and become the solar wind. Solar wind is made up of charged particles, mostly electrons. It goes throughout the whole solar system, and including the Earth, and it interacts with the Earth's magnetic field, which causes the northern lights and all sorts of interesting phenomena that takes place when that happens. Now we're going to be starting to use a Kelvin temperature scale. Your book's using it. Your book may have introduced it. I don't know where, but we need to know what the Kelvin temperature scale is. You take a number of different gases and cool them down and measure the volume. So maybe you take some gas at some temperature and it's got this volume here. You cool it down. As you cool it down, the volume goes down. It's like, why in the winter do you have to put air in your tires? Well, because the cooler air means that the air molecules aren't as energetic inside of there, so that means your volume of your tire goes down a little bit. So you got to put more air in there to increase the pressure. So it basically as the temperature decreases, the volume decreases. So you take some gases, cool them down, and you get a line that looks like this. There's a data point, there's a data point, there's a data point. See where the line goes? It goes right there. Take a second gas, cool it down so the volume gets smaller, there's volume over here. Then extrapolate, complete the line, boom, it hits right about the same place. Take a third gas, do the same thing. Take any gas, cool it down, cool it down, cool it down, get data points. Then continue the data points, and they all meet at this point right here, which is minus 273 degrees Celsius. So let's just call that 0 Kelvin, absolute zero. Nothing can get colder than this. We've already gotten down to 0 volume. You can't get any less than that, right? You can't get negative volume. So that's absolute zero. That's as cold as it could possibly get. If it was 0 volume in the room you're sitting in right now, all the air molecules would be on the ground and they wouldn't even be vibrating. so you wouldn't even have anything to breathe. Okay, so extrapolate back at all the gases. Okay, so we get to minus 273 degrees Celsius. This is the coldest it can get. Call this 0 Kelvin, absolute zero, as cold as it can get. To convert from Celsius to Kelvin, so in other words, you have a Celsius, you want Kelvin, simply add 273 to the temperature. So minus 273 plus 273, that gives you 0. If you had 0 degrees Celsius, what is that? What is freezing point of water in Kelvin? We'll simply add 273 to 0, you get 273 Kelvin. Room temperature is around 20 degrees Celsius. So what is it, room temperature? About 293 Kelvin. Just add 273 to 20. And then what is the boiling point of water? Just add 273 to 100, you get 373. All right, so the sunspots, the sun, starting on the sun now. Sunspots have temperatures in the range of 3,800 Kelvin, someplace around 3,800 Kelvin, which is hotter than the surface of many stars. Notice up here we just said room temperature is only 293 Kelvin. Here we're talking about things that are 3,800 Kelvin. Okay, they only appear dark because they are surrounded by a surface at 5,800 Kelvin. So they're only dark by comparison. If we could take the sunspot off of here and put it out here away from the sun, it would be very, very bright. But because it's overwhelmed, it's got this much hotter surface surrounding it. That's why it appears dark. If sunspots can be isolated, they would appear very bright. They are related to the sun's magnetic field and are in fact formed by magnetic lines bursting through the surface of the sun. So the sun has a magnetic field just like the Earth does. It originates from someplace in the interior of the sun. The magnetic field lines that form because of it burst out through the surface, and then that's what we see as sunspots. Okay, there's a pattern to this. They call it the butterfly diagram, because this is how they would appear on the surface of the sun if we graphed them. This is the sun's equator right here, okay? And so in the beginning of the cycle, they start off far from the equator. See down here, there's hardly any at the equator, but up there, up here. But as time goes by, it's about an 11-year period, they start moving towards the equator. They start migrating down towards the equator, and at the end of the 11 years, they're not up here anymore, they're down by the equator. Then the whole thing starts all over again for another 11 years. Now, one thing that happens, let's say these are all north poles and these are all south poles. In the next 11-year cycle, it switches. These are all south poles and these are all north poles. So maybe it's really like a 22-year cycle instead of an 11-year cycle. Okay, the start far, okay, it should be they. Oops, I've already uploaded this. Anyway, they start from the sun's equator and over an 11-year period slowly drift down towards the equator. But when the next cycle starts, the poles in the northern and southern hemispheres have switched. Again, so if this is all north poles, these are all south poles, the next 11-year cycle, these are the south poles, these are the north poles. Then it goes back to these being the north poles, these being the south poles. All right, so that's what the sunspot cycle thing looks like. It's just magnetic field lines bursting out. So here's a magnetic field line generated someplace in the center of the sun, and they burst out through the surface. So that's what those dark spots are. Now, here's the thing. The sun has differential rotation. It's not solid like the Earth is. In the Earth, it doesn't matter where you are, you're going to rotate once every 24 hours. But the sun, the equator rotates faster than the up here, the northern and southern hemispheres do. The equator goes faster. So the sunspot, those magnetic field lines get all twisted around. And somehow when they get all twisted around, it kind of stops everything, and the whole process starts over again. So it goes here, maybe this is year 5.5 years, this is 0 years, 5.5 years, and we're getting close to the 11 years where they're all twisted around, and we get back to this. So that's why the sunspots kind of start far from the equator, then migrate down towards the equator over those 11 years. Okay, that's it. That's it for this one. Okay, so here is the online lecture we got. How old is the sun? Well, we got it in there. It's about 5 billion years old. About 1.3 million Earths could fit in the volume of the sun. Okay, the most abundant element in the sun is hydrogen. We got that from that table. Second most abundant is helium. We got that on that table. And if you want to draw the sun, you simply go to this picture right here. Has got it all. There you go. It shows you everything. This is in your book, in the book. Okay, the outermost part of the sun, that is the corona. But the part that we actually see is the photosphere. Photosphere, chromosphere, corona. We don't see the corona and the chromosphere just by looking at the sun, glancing at it when it's overhead, or looking at it a little bit longer when it's rising or setting. We actually see the photosphere. Okay, what part of the sun is energy generated in? It's generated in the core. That's where the sun is converting mass into energy. The two methods the sun makes use of to transport energy to the surface, those are the two zones we talked about. The convection zone's at the surface, then the radiation zone transports energy from the core up to the convection zone. What makes the Kelvin temperature scale different from Celsius and Fahrenheit temperature scales? Well, first of all, there's no negative numbers. Okay, 0 is absolute 0. That's as cold as it can get. Then how was absolute 0 determined? We had gases shrink, and we saw how their volume got smaller with lower temperatures. We said, okay, at what temperature would this gas go to 0 volume? And we did that for a bunch of gases, and we saw they all kind of go to 0 right around minus 273 degrees Celsius. So we called that 0 Kelvin. What causes sunspots? Magnetic field lines bursting through the surface of the sun. Why do they appear so dark? Because even though they're very hot, 3,800 Kelvin, in actuality they are surrounded by 5,800 Kelvin of sun surface. So that's why they appear dark. Okay, I think that's everything for this online video, whatever you want to call it. Again, if we go over to, see, I just had it up here. All right, so here I just uploaded these guys. I'm so confused. It's telling me the students have already turned on online lecture 6, and I thought I didn't have any place where you just turn it in. So I don't know. I'm confused. All right. Well, anyway, if you haven't done online 6 is the other one. It's this one about the telescopes. And you're gonna have your quiz about the telescopes on Thursday. Okay, I'll come up with a quiz on Thursday. Then on Tuesday you'll have a quiz on basically what we covered today, and if I can get a video out, I don't know about tomorrow, but maybe Thursday, and then more videos over the weekend, and then our final exam's got to be, I think, Thursday of next week. I got to go look again, but I think that's the 8 weeks. All right, so anyway, we've got all that, and then this PowerPoint has been uploaded. PowerPoint is here, Chapter 15, and the worksheet for Chapter 15 that we just looked at is right here. And then I made the due date 27th, which is next Tuesday, I believe. And then we'll have a quiz on Tuesday too. Okay, I think that's everything. I'll send out I better send out a blast email now. Okay, so I'll talk to you later. Good night.